All right. Hello again, everyone. This video will be about the work-kinetic energy theorem, as you may have guessed already from the title. So, in the examples and the problems up until now, we've only dealt with forces on objects such that their displacements are only in one direction, right? In other words, nothing's changing really. That's a rather simplistic example or simplistic situation. So now let's kind of take that into the more generalized situations, right? What I mean is, what if you were trying to push, say, a skateboard up a half pipe, or a snowball up a hill, or some object, right, up this circular, half circular surface, all right? So your intuition may tell you that the easiest way to do that is to always have your force in the same direction as it's moving, right? The force in the same direction as the displacement. So let's say you apply a force in blue here, F, right? The displacement at that point, at least, would be pointing also in that direction, right? Whoops. For right now, I'm going to use the notation of R, right? This is actually the general displacement symbol instead of D, okay? So your intuition should tell you that in order to most easily push this object up to the top, so actually let's start at point A and end at point B, you should always have your force and displacement in the same direction, okay? But what if you wanted to make it harder on yourself and always use the same vector force, right? In other words, what if the object was about halfway up and you have the same force, F, pointing that direction? Which way would it be moving? Well, this is, you can assume it's an impenetrable surface, so it's moving along the surface, or tangent to the surface, in other words, at that point. So notice that the r vector has changed. It's not the same as what it was at point A. It's changed. And if you wanted to make it even harder on yourself, you could continue using the same force vector F all the way at the top. And the displacement vector here would be pretty much straight up. Okay? And so if we extrapolate and fill in the gaps here, in between, if we use the same force, F right there, and right there, something like that, and displacement would follow that pattern, right? It would always be parallel to the curve at that point. Something like that. Something like that. Okay. So in this situation, this would do far less work. In other words, it would be much, much harder to move this object from point A to point B, because the component of the displacement R is, the component of R in the direction of the applied force is decreasing from point A to point B. So that's why you're doing less work in this situation, and thus it would be harder than if you always kept F and R in the same direction. Okay? So, saying all that, what if you wanted to find the total work that you did in moving this object from point A to point B, right? The total, not just at one point, but the total work. Well, assuming that the magnitude of this displacement, R, always stayed the same, you can see that the components, right, X and Y, change. So that means that the work done at every point is different from every other point, right? Let's take a little closer look. Previously in this chapter, we've defined work as basically a force times a distance. And I've written it as D in this case, right? I'm going to write it as R because you'll see in a second I don't want to keep using the variable D. So a force times a distance. I guess I should write it in general, the r vector is x plus y, right? Just a brief aside. Okay, this is what we've been doing up until this point, right? But in this situation, we can see that the angles change. The angle is actually getting bigger and bigger up until an angle of 90. So can we simply write, if we wanted to find the total work, can we simply write this? No, we can't, right? The magnitude of force, that can be constant. The magnitude of r, that can be constant, right? But the relationship between the two, in other words, the angular relationship, that is changing. So if we wanted to find the total work simply from, say, this expression, we can't do it. We have to come up with another expression. Well, you all have taken calculus. We need to integrate. Okay? We need to integrate basically from point A to point B. But that expression above, the force dotted with some displacement. Okay? And in this case, you can write d theta if you want, but you cannot have the dot product notation. So let's leave this very general and leave it as a dr, right? A force dotted with some differential displacement. And that means that at every point along this surface, you can think of very tiny, infinitesimal, tiny r vectors, right? The differential vectors, each with their x and y components, right? dx and dy, something like this. So if that's dr, this would be dx, and that would be, of course, dy. And so if we move from point A to point B, both these magnitudes, dx and dy, are changing continuously, okay? Because, of course, that's a smooth curve. So now, let me write that work into both x and y directions. We have the same force, now dotted with dx, and a very similar expression for the y component. And so now what I've done is that I've broken up the general work expression, right, into just the work done in the x direction and just the work done in the y direction. Okay, so if you wanted to, work x and work y. And so if you wanted to, you could evaluate this expression written as is, right? If you're given a force, the magnitude, plug it in. If you're given the length of x, well, that can really change, right? The component of x will change throughout the motion. So you can't really plug in a set number for dx, much less theta. You can integrate from 0 to 90, but you don't know the dx distance. So let's write this an easier way. Okay, I'm going to plug in Newton's second law here, F equals ma, and I'm going to plug in for dx, right? And dy, same thing. So I'm going to use the definition of velocity rather. I'm going to say dx equals velocity times dt, right? Distance equals rate times time. So now using both of these expressions, we can rewrite the integrand here. And you'll see that if we do a little more algebra, it'll turn into something a lot more manageable, right? A lot more, it'll be easier for us to work with, in other words. So, all right, work in the x direction from A to B. The force, this is again the force in the x direction, so we have to do mass times acceleration in the x direction. The dot is still there. Now, plug it in for dx. We said that was now velocity in the x direction times dt. And I'm doing the same thing for the y direction. F was mass times acceleration in the y direction now. plus velocity in the y times dt. Okay. We can even rewrite acceleration here, right? We can write that in terms of v and t. Let's do that. We have mass. Acceleration is change in velocity over change in time. So in calculus speak, that's dv dt. And this is in the x direction, so we have to be consistent. The dot stays there. We haven't evaluated the dot product yet. Then we have Vx and dt. That stays the same. And now look what happens. The differential time goes away. dt is on both top and bottom. So that cancels out. Same thing happens for the y direction. Let me just write that real quick. Dot Vy dt. The dt's cancel out as well. And now we can rearrange this integrand a little bit. Mass, assuming that mass of the box or the snowball or whatever stays constant, we can pull that outside to simplify the integration. And now we have to evaluate this dot product here, right? And by evaluate, I mean take the magnitude of. So let's do that. That means we take the magnitude of both the first times the magnitude of the second times cosine of the angle in between. So I'm going to actually flip, but it's okay because they're just the magnitudes. So we have the magnitude of both, right? Vx times dvx. And then what's the angle in between these? Right? This is, Vx is the component of the velocity of this box as it moves from point A to point B. It's the x component of the velocity. The dvx is the tiny bit of change, right? It's how much that velocity component changes in the x direction. Well, if they're both in the x direction, the angle in between them is 0. So thus, cosine of 0 is 1, and our integrand is just v dv. And that we can do. All right, pulling mass out again. Oop, squeeze it in there. Same thing for the y direction. dvy, and then cosine again of 0 is 1. And so this is simply the y component of the velocity. There, 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 and there. That's changing. dvy is the differential bit of that velocity component. Okay? So if we keep going, we can now evaluate this integral. We have mass. Actually, let me do it here. We have integral v dv. That is Vx squared over 2 evaluated from A to B. There's no vectors anymore in this. It's simply a magnitude, right? We do the same thing for the y direction. Okay. Again, this v squared over 2 comes from simply integrating Vx with respect to dvx, right? Don't let the subscripts throw you for a loop. They're just part of the variable, if you will. And so mass, I'm going to bring the 1/2 out. Now we have simply v. I'm going to do it like this: v final squared minus v initial squared. That's all in the x direction, right? So this point B is the final position. Point A is the initial position. Well, that's simply a delta V squared. That's all that means. It's a change. Doing the same thing for the y direction. Let's do that. Minus V. And that's in the y direction. Also, a delta V squared. And so if we have the change in speed squared for the x and the y directions, we can combine this with the Pythagorean theorem and say that, well, all of this is simply equal to VB squared minus VA squared. Well, that's simply the total change in kinetic energy, right? This is what we mean by kinetic energy. 1/2. Kinetic energy is in that form, right? So in other words, kinetic energy is 1/2 mv squared. 1/2 times the mass times the speed of the object squared. That's the form of what physicists know as kinetic energy. It's the energy of a particle's. If a particle is in motion, that's how much energy it has. And so this entire process was getting us down to this point. The work done by a force as it moves from some initial point to some final point is simply equal to the change in its kinetic energy between those 2 points. That's it. So you can do this for every type of force, right? And then you can simply add them all up to get the total work done, which should equal the total change in kinetic energy. But this is known as the Work-Kinetic Energy Theorem, and it's very, very, you can say it's an elegant derivation, right? Because it simply boils down to W equals delta K. That's it. So we start out with this mess, plug in some equations from chapter 2, and then we get it down to work equals the change in kinetic energy. Thanks for watching.